Hello, everybody. Welcome at the last session of this year, where we are going to talk about broken tools. And first of all, because this is a live broadcasting, and people always say you have to feel sympathy for the subject you are talking with. If I suddenly start bursting out coughing, sorry for that. I have a big cold, but at least I start doing that. I feel a little bit how it is when something breaks. So tool breakage, broken tools. We all know it. We all are confronted with it now and then, and very often people consider it a bit as an annoyance. Yeah, it's not fun, a broken tool. But people also have a tendency of kind of not giving it the correct attention, because normally people say when a tool breaks, a broken tool is an accident. What can we say about an accident? The best thing to do is you take the broken tool out, you put a new tool in, and you continue. Now, I think that's a little bit too simple if we want to do it in a more correct way, because a broken tool, first of all, it's a lot more, when you talk about cost factors and impact and so on, it's a lot more than just having to buy a new tool. Because a broken tool costs you a lot of time, production time, because you have to take out, put a new one in, do the setting, correcting, and so on. It's costing you not only money to buy a new tool, but you lose machine utilization time, and that is money, and you are energy, and the production flow is interrupted. So a broken tool is a lot more than just take it out, replace it, and continue. And the session of today is not especially about only how can we avoid it to break a tool, because to some extent that's nearly impossible, because in a lot of cases indeed a broken tool is an accident, and how to avoid an accident is but from that accident we can learn something, and see it like this. If somebody falls down the staircases and breaks a leg, goes to hospital or is brought to hospital, a doctor can say, okay, you fall from the staircases, you broke a leg, I do some stuff up, it's taken care of, let it heal, that's it, it's an accident, it's a pity. Another doctor could look into it and say, okay, you fell down the staircases, you broke a leg, but he could look a little bit deeper and see who is this person, what's the age of this person, is there a medical background to this person, because perhaps the fall from the staircases was not so severe, but there were some other underlying reasons why that person broke a leg or an arm. And from the event, a broken arm, a broken leg, suddenly we could find out something much more severe, much more structural an issue. And it's that second approach I would like to do here with you. Accepting, when a tool breaks, it's an accident. And in a number of cases, it is an accident. And accidents do happen, unfortunately. But in a number of other cases, you can say, okay, it's an accident, but it's type of an accident you saw coming. I mean, if you decide to use your phone while driving and you end up in an accident, you understand what I mean. This is an accident you saw coming to yourself by the things you were doing before. My name is Patrick de Vos. I'm your host today for this subject, and in all the years I worked in machining, I kind of developed my own approach to machining. And if you look to a machining process, a good one that is in balance, one that is in control, it demands a lot of stuff from the people doing it. You need the knowledge, you need insight, expertise, you need experience, you need to understand what's going on. A lot of domains you have to master to master this process. But even then, what we see in machining is that every ship which is formed, every used tool, every workpiece, or not every workpiece is correct. A big number of workpieces are not correct after the process. That means in machining, there's still quite a lot of chaos. And part of that chaos, and chaos is you kind of have a situation which is unchanged. You have the same tool doing the same operation in the same workpiece in the same material, yet the result is different. Suddenly a tool breaks, and the operation before, or the workpiece before, it didn't break. Why did it break now? That's kind of chaos. To be do something useful with that, and I already said it a couple of minutes ago. You can accept it, or you can try to learn from it. And there are methods, systems, concepts that allow us to learn from ships. At the previous session, we already talked about ship control and how to manage that. We already talked about used cutting tools and what can we learn from wear phenomena. Well, today we are going to do kind of the same approach. Look at the situation. And in particular, I would say the photo you see directly here behind me, used tools. In every workshop, you have the bin where the used tools are collected. It's always interesting to have a look in that. And by sentiment, what do you think? If you look in that thing, see the photo behind me here, how many of the cutting edges there? And put it in the comment. I'm always interested to learn from what people think. These tools are classified as worn out. They have so much wear, they become unusable. But part of these tools are broken, or part of the cutting edges are broken. Any idea how much? How many of the used tools ending up in the recycling bin are in fact broken and not worn out? Because there's a difference. We are going to come back to that. For people who want to know more, because we have only 1 hour together, and 1 hour is not so much, even if we want to talk about a little thing like broken tools. But we'll quickly figure out that there's a lot more to say. You know that there are the pocket guides, the series of pocket guides on several subjects. There's also a pocket guide on broken tools. With practical stuff around it, how to handle, how to take care of it. And as always, I'm of course not alone. I have the honor of presenting this, but there are 2 girls in the background taking care of all the technological stuff to make this happen, to make this possible. Alesia and Margarita. And why a special session on broken tools? As I already said, in a lot of situations, people in a workshop say, it happens, let's not overdo it. Well, there are some stuff we have to remember. First of all, a broken tool is more than a broken tool. A broken tool is not just replace it by a new one and continue. There are, from a strategic perspective, implications on your production. You interrupt the production flow. And if you interrupt in an unplanned manner your production flow, at the end of the line, you have an unhappy customer. That is unhappy because you didn't keep your promises, because you delivered too late, because the quality of what you delivered was not in line with expectations. Perhaps because you tried to have some extra money back for all the tools you broke. So don't underestimate the impact of a broken tool. It's more than just a broken tool. Important, if we talk about this, is that we make a clear distinction, because what we call tool deterioration, and deterioration is the collection of phenomena leading to that a tool is not capable of doing its job anymore. which is cutting metal in a balanced, controlled manner. You have tool breakage, that is a tool that breaks. And you also have a tool crash. Partly the result of a tool crash is, of course, also a broken tool. But a broken tool as such or a tool crash are two very clearly different phenomena. And we have to make the difference directly when we talk about these things. The third thing why we have to be careful with these things is that people sometimes underestimate the impact of broken tools when you look into the numbers. 2 slides ago, I asked you if you see the photo with all the used tools. Any idea about how many of the cutting edges you see are broken? Well, in small batch production, what you see is that if you investigate it really, truly, that around 30% of the cutting edges which were used end up their useful lifetime as broken. 30%, 1 out of 3. I wouldn't call that a minor phenomenon. Now, by sentiment, people say 30%? That's a lot. But by sentiment, and we come back to it, I have done so many projects on this. You know, when a tool breaks, for an operator, an engineer, a production engineer, it's an event on which he feels ashamed. They take it personal. I would take it personal if the tool I'm using is breaking. That means that there is a certain unwillingness to communicate about it. And that means that from a purely human communication perspective, people are not always aware of how big this thing is, broken tools, until you take the bin with the used tools and you start counting. And then you find out that it's bigger than everybody thinks it is. Tool breakage, tool crash, we can be very quickly about it. Tool breakage is the phenomenon. I'm using a tool, it's in use, we are machining, and it seems everything looks good. And then suddenly, while being in operation, the tool breaks. And the process kind of continues. The machine continues to operate, but the tool is broken. The result of that phenomenon is a broken tool. Now, what's going on here is that it could be an accident, in a sense of that, take the example that you are machining precipitation hardened materials, and that the cutting tool by coincidence hits a precipitation hardened spot, and you suddenly have a peak load on a cutting edge that is bigger than the load bearing capacity of the cutting edge, and it breaks. Then it's purely an accident. It's one possibility. Another possibility is that you started from the beginning with or a tool or cutting conditions or cutting data which were not in balance, and that slowly, progressively, you were overloading the tool until you reached the level that the tool couldn't handle it anymore and it broke. Second possibility. There could be a third possibility, and that is that due to something, the tool is suddenly overloaded, kind of not mechanically, but due to too high temperatures, a ship which collides with a cutting edge. You have double cutting of a ship, and that creates a situation that the tool can't handle, and it breaks. So later on, if we look to broken tools, what we also have to dive into is try to have a clear understanding. Okay, this event took place. The result is a broken tool. But what was it? Because how we handle it afterwards will be different depending on the actual phenomenon that took place. Tool breakage is failure of a cutting tool itself. It has nothing to do with the machine or the work. It's the tool itself that fails due to an overload. An overload that was built gradually, or an overload that happened at a certain moment in time. Tool crash. That's a situation which is quite different. That's a collision. The tool hits the workpiece or something else, a clamping device, part of the machine table. I don't know. The tool hits something it's not supposed to hit at the speed, at the feet, or at the direction which is no good. With other words, tool crash is an error in programming. You made a tool movement which was incorrect. And that can be a human error, that can be an error in the NC program, that can be an error in the setting of the tool, that the length setting or the diameter or something was wrong. But the result here is an instant crash, an instant stoppage of the process. And the damage here is much, much more severe, because here not only the tool is broken, but you also risk that the machine is damaged, that the workpiece is seriously damaged. This is very much something else. So our first message, kind of those amongst you who are interested in starting to look a little bit more structured in this, is that you have to instruct your operators collecting the tools, that a broken tool, there should be 2 boxes for broken tools. 1 box for tool crashes and 1 box for truly broken tools. Truly in the sense as I described, tool breakage as part of a process and so on. A sudden unintended collision between the tool and the workpiece or the machine or something else is called a tool crash, and the result of a tool crash is also a broken tool, amongst others. Tool breakage is about the process dynamics, where we have to look into. Tool crash is human or programming error. A tool crash, I could say this is truly an accident. And from a tooling perspective, if you have a tool crash, the only thing to do is to replace the tool. It's not about a tool which was not working well. It's purely a programming error. Why do tools break? A lot of people say, tool breakage, it's random. It happens sometimes. I think it's often predictable, but people fail to predict it. As I said, if you decide to use your cell phone, while driving, you are heading for an accident. It's not random then. Don't call tool breakage a rare phenomenon. Don't call it a random phenomenon. If you really look into, in a lot of cases, it's predictable. And there are, in all my years in machining, I learned that there are kind of 4 main reasons identifiable that leads to broken tools. And every broken tool is willing to give you the message, if you know how to listen to things, that is this something that has to do with wrong selection of tool or wrong combination of cutting tool, workpiece material, cutting condition. With other words, where your starting conditions wrong. You brought together a tool and cutting conditions and whatever that couldn't work. Is one reason. Tool overload. It can work, but somehow you went too far with something, and that led to a tool overload. And that over time led to a tool that couldn't handle it anymore and broke. A third reason is plainly wrong using the tool. If you have a certain tool with a certain capacity for depths of cuts and feeds, and you go beyond that, yeah, of course you will break a tool, obviously. Or using the tool too long. I give you a number. Everybody knows about flank wear. Everybody talks about flank wear, and people measure flank wear, and there are sayings about flank wear should be maximum this or that or whatever. All kinds of figures are floating around. But what people do not are always aware of is that if flank wear increases by 1/10 of a millimeter, the cutting force acting on the cutting edge increases by plus minus, depending on the material and stuff, but plus minus 10%. That means if you give your operators an instruction that they have to replace a cutting edge when the flank wear is 4/10 of a millimeter, one of those figures you hear now and then, that means that by the moment they reach that 4/10 flank wear, the initial cutting forces are already 40% higher or increased, and that are the the cutting forces you will have at the moment you have 4/10 flank wear. Now, if your initial cutting conditions were already as such that the tool was on the edge of its possibilities, and you want to use it till end of tool life, 4/10 flank wear, with other words, cutting forces which are 40% higher, well, in between, most probably you already broke the tool. That's what I mean with using the tool too long. Or process instability. That's the fourth big family. Wrong selection, wrong combination of tool and application. Yeah, what can I say about this? This is before you start machining, do your homework is kind of what I would say here. Do your homework in an intelligent way. Because the last years, very often when I talk to people and if I ask them, yeah, but these cutting conditions, couldn't you imagine that this was going to turn wrong? They say, yeah, but no, I don't know. I used the software from the supplier, and that software told me cutting conditions X, Y, and Z, and that's what I used. So be careful with that. Just copying what you see on a computer screen or something. Think a little bit. Try to understand the cutting tool, I would say. It can be wrong expectations. Yeah, but I thought, I supposed. Yeah, supposing is in a big number of cases the reason tools break. Tool overload. This is about knowledge. This is understanding that the cutting process is something where a tool has a load bearing capacity, and the process put loads on the cutting edge, and that those two needs to be in balance. And that can be mechanical, that can be thermal, that can be tribological, that can be chemical, that can be concerning ship formation, whatever. Nobody ever promised you that the machining world is an easy world from a scientific perspective. But this is about understanding what you are doing and making sure you use the tool within its capacity. Overload is a sneaky one. You don't hear that, you don't see it. The tool seems to work. Until it's too much. And then the tool breaks. Wrong use of a tool. The tool itself is okay, and it's okay for the application, but somehow you selected a finishing cutting geometry, and that is what you needed for the application, but the cutting data you use are typical roughing cutting data. So it's a wrong combination. Wrong use or use too long. I already said, think on as a tool wears out, things are changing in the process. Cutting forces go up, more heat is generated, and that leads to after a certain time you have an overload. The wrong savings. I call it the just one more part syndrome. The tool is showing where, but I think it'll do the next part also. Yeah, very often it doesn't. and then you have a tool breakage. That's the false economy part. And then process instability. Everything that influences how the process is running in a negative way. Excessive chatter, unstable work holding, spindle run out, improper cooling, tool parts which are not okay. All of these things create an unstable machining process, and that somehow will lead to a tool that in the whole chain, the tool is very often, or the cutting edge is very often the weakest part, and it breaks. So if you have a broken tool, which is not a tool crash, but a truly broken tool, one thing important, try to put it in one of these 4 families. To be able to do that, people need knowledge. People need to understand that the machining process is not magic. I think sometimes people think it's magic, but it's not magic, it's science. It's science and technology. And if we understand what's going on, you can understand why a tool reacts as it's reacting in certain situations. It's about skills, because understanding and understanding the why and knowing what to do, you also have to be capable of knowing how to do it. And I call that skills. But it's also motivation. And it's one of those things, as I already said, for a lot of people, a broken tool is something to feel ashamed of. And that makes that a motivation to openly try to find a solution is not always really present. Very often people, it's good enough, and 1, 2, come on, I broke one drill, what's the problem? Or it's not my fault, the next one can take care of it. I did that once at a customer, I spent a day in the tool crib, the tool room where all the tools come back or come in, and looked just at the tool that was handed in with no comments. How does this tool look? You can't believe how many broken tools are handed in with no comment. Yeah. Broken tools are important. Broken tools is much more than just a tool that breaks and you need to buy a new tool. It's lost time, extra cost, frustrated operators, unhappy customers, delivery that is not respected, production pace that is going all over the place. It's broken tools are a big thing. And as I said, in a number of cases, we cannot avoid it. If a cutting edge hits by coincidence a pH, a precipitation harness spot in a workpiece material, and you have a peak load that breaks the tool, you can't do anything about it. You have to learn to accept that. But in a big number of other cases, it's predictable if you know how to predict it. And that is something we can learn from the previous tool that we broke. If a tool breaks, there are 2 things at least you should try to figure out. One is, where did the tool break? And there are 4 possible spots where the main breakage takes place. The tool point, the tool body, the tool, the cutting edge and the tool body. I was trying to, if you have an insert type tool, it's or the cutting edge on the insert or the insert holder, the tool holder, the milling cutter, body, whatever. And the tool shank, the part where the tool is clamped, gripped, and connected to the spindle of the machine. Point of the tool that breaks. If you see that the breakage is there, and this very often will not be a very catastrophic breakage, but it's kind of, the little point is broken off, the point is blunted a bit. That is what you see there. That has to do with entry. Somehow you created entry positions for the tool point cutting conditions, tool path, whatever, that are overloading the tool point. And that is where you have to find the solutions also. Very often when tool points break, the solution has to be found in machining strategies rather more than in the tool itself. The actual cutting edges is a second area where you can find breakage. Here it can go from micro-shipping over flaking to really big parts breaking out. This has to do with wrong process conditions mostly. Feed speeds are not correct. Could also be hard spots in the material that create a problem. Could have to do with heat and temperature, cooling conditions. That are the main reasons here, or that is really what you have to look into. If you have the tool body, let me call it like that, in case of an insert system, it's really the milling cutter body, the turning tool holder. If you break that, or it's a general overload of the tool. It's not just locally some overloading. The tool itself is totally overloaded, mostly mechanical. Or it can be that the tool is too weak for what you ask the tool to do. And meaning that it starts bending, vibrating, you have fatigue phenomena starting to take place and stuff like that. And then you have the fourth area, the tool shank. This has lesser to do with the cutting process itself, with the exception that, if the cutting conditions are as such that the total process is in overload, somehow you will damage the shank also. But very often when a tool breaks in where it's clamped, it has to do with the actual tool clamping. The tool clamping devices, the collet chucks, the shrink fit all, whatever you use in case of a milling cutter, or on a lathe, the clamping mechanism that you use to put the tool holders in the turret. It's mostly in bad maintenance, bad condition, wrongly used, too high torques, too low torques, stuff like that. This is lesser machining process. This is more tool manipulation issues. So if you stand there with a broken tool, first thing, where is it broken? Point, cutting edge, body, shank. 4 different things. And I dare to say easily recognizable, I think. The second thing, not always so easy, is when did the tool break? Immediately? Within seconds, the operation started? Somewhere during cutting? Or after a while when the tool started to approach end of tool life? Immediate break, the tool hits and breaks. And if it's not a tool crash, that's the distinction you will have to make here. It's not a tool crash. Everything is well programmed. Everything is as it's supposed to be. Yet the tool hits and breaks. That's wrong data. It's an instant overload of the tool. That means your cutting data are or wrongly selected, wrongly chosen, or wrongly programmed. Can also be. Mid-cut, you are cutting and suddenly everything seems okay, nothing to worry about, and the tool breaks. I would say it's all the workpiece material. You hit somewhere a hard spot or something, but most probably it's more something about the ship evacuation. You had somewhere a ship evacuation building up situation with ship evacuation that led to somewhere, you had the blockage and that broke the tool. If you have that, it's you have to look more to the ships and how they are formed and how they are evacuated. End of life. I'm going to come back to that in a few slides. Now, a lot of the things I'm telling you here is not just wisdom from books, because for a big number of years, I have been doing, and not only me, a lot of people are doing, what we call GTDA approaches to toolware, global tool deterioration analysis. And what I learned from that is that very often we like to blame the tool. Bad insert, wrong insert, no good insert, bad milling cutter. While it's not appropriate to say that, because tool deterioration, and as I said, there are I don't know, hundreds, thousands of situations where we dived in and where we try to understand what's going on now. And of course, if you want to do this in a more structured way, you need the knowledge about how do tools wear and how are the loading phenomena and so on. And then it's a very straightforward approach. You take a batch of used tools with as much information as possible available with it, and you analyze the whole thing. And if you do a situation like this, and I give you just here an example, what you see is there are two phenomena very important to understand. In the diagram, I don't know if you can read it, but the text is less important here. I just did a copy-paste here, didn't change anything from one of the reports we made. The second one from the right is tool breakage. And the blue one is what we call industry standard, what would be good practice. And what you see is, if you look to tool breakage, that the industry standard is around 10%. That means that good practice for tool breakage is that we accept 10% broken cutting edges. First of all, it's something I want to underline, because sometimes people are dreaming. They think, if I dive into this, we will end up in a situation that I never ever will break a tool anymore. Now, no, there still be accidents. But what we also see, even with that 10% taken as an industry standard, in the majority of cases, in this case, number of broken cutting edges is 19%, double. And that, of course, is what I said a couple of times now already, and here confirmed by reality. Avoiding that a tool breaks, difficult. Learn to live with the reality, my industry norm here, 10%. But the reality is also that at first sight, if you measure really, you find that it's a lot more. In this case, twice as much. But by learning from these cases, we can try to bring it down to the 10%, which would be acceptable. That's the whole reasoning here. And if you dive a little bit more into that, here you see the same numbers or the same evaluation we did. But here also, if you look to wear, we split it out into normal wear. I mean, we let the tool wear out till normal levels before we decide to replace. Or we have excessive wear. There's just one part more syndrome. I did handle it. It will work. Which ends up with tools showing too much wear. Or the third column, hide it behind me, but now visible. The third column is the very careful people. They say, let's stop now. I think it has been enough. And that is the too low wear. Sometimes too low wear. Yeah, it's too low wear. You could have done more, but out of carefulness, you decided to stop. Now, what you see is that the more you go from too low wear, you understand what I mean with too low wear, to normal wear, to excessive wear, The more you go in the direction of excessive wear, the more you see popping up also broken cutting edges. In this evaluation where I said 19% of the cutting edges is broken in general, if I make another split, 60% of the cutting edges that indicated too much wear are also broken, while 0% of the cutting edges that show too little wear are broken. So it's kind of also here, it's a balancing exercise. If you stop too early, I think you throw away money. You could have done more, but okay. And the more you go to normal, but over normal, you try to save some money and say, one part more with this tool, and then one part more, you are going to start losing money seriously because you are going to start breaking cutting edges very fast now. And that is also a learning point here. Where do we stop? How far do we go? Now, interesting also is the human aspect here. If you ask operators about broken tools, and it's a serious thing, operators will tell you, it's a blame for me. I don't like it. I look bad. People think I don't know what I'm doing. So operators have a tendency to hide a bit because they feel ashamed about the phenomena. Engineers, most of the time, what I take here is a collection of quotes I picked up in workshops. Engineers are very often more pragmatic. They say, okay, tools break. We know tools break. It shouldn't happen, but let's learn something from it. It's not nice, it's not fun, but okay, let's try to do next time better. What happened? So next time we can do better. That's what I pick up. That's mostly how engineers react. Bosses, managers, they are quite different. They say, broken tools, impossible. We don't break tools in our workshop. They don't believe it very often. And you see here a problem arising. Managers, bosses, they say, no, we don't break tools. At least nobody told me we break tools. And of course the operators don't tell them because they feel ashamed. So there's a very important task here for the engineers to bridge these two, that managers start to understand that tools do break, even in their workshops, and the consequences of it. And that operators learn that they shouldn't be afraid of admitting the tool broke. Because otherwise, if you hide it, how can you ever learn something from it? And that role is for engineers. Some extra statistics I dived in and tried to figure out here and there, some figures and so. First of all, what I can tell you is if you try to find out information, data, statistics on broken tools, it's very difficult to find something which is really valuable. In general, what I found is that tool failure, tool breakage, and it's also something I learned with GTDA projects, 20 to 40% of the unexpected downtimes of machine tools are due to tool breakage. Now, if you know that in small batch production, unplanned downtime, unexpected downtime can count for 30% of the time spending, and if you say 40% of that 30% is broken tools, that means in the overall picture that you lose 10% machine capacity due to broken tools. 10%, people. That's 1 hour per day. Very fast calculating. So don't underestimate the broken tools. The hiding aspect in small batch production, the so-called worn-out tools in the recycle bin are in fact broken tools. But yeah, no comment. Tool breakage is expensive. Huh? I found one study from Fraunhofer Institute in Germany where they try to figure out if a tool wears out and is replaced, what's the cost for it? And if a tool during operation breaks, what is the total cost for it? Well, depending on the situation, a broken tool can give you a 10 times higher cost factor per incident, per accident, than a worn out tool. 10 times more. So it's not just buy a new tool and that's it. And I found two studies, one Scientific Coromant and the other AMRC, that state that 50% of the breakage incidents with cutting tools refer to human error. Now, I cannot confirm it or not. It's just something I found. But it's intriguing that on the one hand, managers think we do not break tools. On the other hand, if you really dive in, it seems that 50% of breakage refers to human error. And you remember my thing, I feel ashamed and people are going to blame me. It's a serious thing. Root causes. Why do tools break? You have the physical causes, the mechanical stuff, overload, ship jamming, wrong tool selection. All of this is hard, identifiable, correctable, whatever you want to call it. You also have the soft causes. If you believe what AMRC says, 50% of broken tools refer to human error. Well, here you have the list of reasons what could be the underlying stuff of so-called human error. Inexperienced people with no knowledge, improvisation, too much stress, pressure to things, stress. Here you have take care of this and you take care of half percent, 50% of your broken tools. Treating broken tools as normal is a strategy. But I don't think it's a good one. Do you? Because a broken tool goes far beyond, I hope you in the meantime are convinced of that, goes far beyond a broken tool. Replace it. Your process efficiency, your process reliability is affected by it because you have unplanned downtimes, you have broken parts, scrap parts, repeatability goes away. And in the end, all of this brings you to that final stage, the unhappy customer. Quality of output. Each time a tool breaks, even if you say, damage is minimum, but there is a risk that your workpiece is somehow damaged and that you need to rework it, repair it, whatever. Cost and profitability. It's not only the machining cost, it's the scrapping of the workpiece cost, it's the overtime, it's the delivery, it's wasted investments, it's wasted machine utilization time. So it goes so much further than just a new tool. And of course, sustainability, that goes together with cost and profitability. You waste workpieces, you waste tools, you waste time, you waste people, the stress factor for operators, and so on. Tool breakage, it's difficult, but I mean to quantify exactly, but operators, machine operators, their stress levels, there are lots of things, but broken tools are a major reason for stress factors at operators. And that means that their attitude, their behavior is going to be seriously affected by it. The least is hiding from it because they are afraid to be blamed. But it ends up with low motivation, not caring anymore. So if you have a feeling that there is something, talk about broken tools with your operators. Bring it on the table. Uh, it's a bit of a dilemma, but handling broken tools, it starts with prevention. Prevention from the beginning, I mean, it starts with selecting tools, selecting cutting conditions, make sure that everything is correctly done. It's about or using systems that helps to predict tool path simulation, collision analysis, that type of stuff. Uh, while you are machining, it's about, yeah, you can use sophisticated stuff, sensors and stuff, or you can try to motivate people around the process to take an active role in this. Even a broken tool, look into it. Well, is it broken or is it a tool crash? When it's broken, where is it broken? When did it break? That type of stuff. Use GTDA principles to do the follow up in this. Make sure your operators have checklists or routines to follow if an event takes place. And that is about training them and giving them hands on stuff they can use to work with. Because broken tools, I think it's in machining, it's a serious thing, but somehow people do not take it in a strategic manner if they look into how to improve production. And I think that's a failed opportunity. From a tactical perspective, if you have a tool breakage, yeah, stop the bleeding. I would say do some things instantly to minimize the negative results. Make sure your process is as safe as possible from there on. Yeah, no more harm than is done. Find the cause. What happened here? Don't just hide it or do it under the table. Take some time. What happened? Based on what you observe, decide and act, and do the best possible to prevent that it reoccurs. Tool breakage. What I try to say here is that in this presentation, tool breakage is a lot more than just a tool that is broken and that needs to be replaced by a new. And there are so many hidden costs here in time which is lost and money which is lost and quality which becomes variable and people that are stressed and so on and so forth. And in the head of people, it's kind of a change in mindset. It should be, people should not think anymore in terms of it's a broken tool, but they should start thinking on this is a broken process. Here I have an interruption in my process. And that is a much more severe thing than just a broken tool. If you look to worn out tools in the recycle bin, what you find is tools that show normal wear, the top row here. You find tools that show normal wear but too little. That's the bottom line in this diagram. For each, the gradual tool wear normal development or the premature tool change with too little wear before the tool is changed. You find here some directly related costs, hidden costs, what it means in production losses and the cost impact. Next to those two, I have been talking today about the two rows in the middle. One is catastrophic tool crash. I didn't talk so much about it because this is really, this is a mistake, an error, an accident, and it has nothing to do, basically not with the tool, with the exception perhaps of the tool setting, length, diameter, that type of stuff. But this has to do with tool movement in or around a workpiece. This is programming. This is human error in the programming. This is the CAM program that went somewhere berserk. I talked mainly about the sudden tool breakage. The second column, the second row from the top. And if you look to the last column directly, all the other details you can read for yourself. Cost impact, normal wear, too little wear. The impact on the cost of that is, it's there, but it's not really severe. But the two columns, or the two rows, sorry, in the middle there, you see that the impact on the total production cost is high to very high. Only based on that, we can already say, please give tool breakage the place it deserves. It's not a minor thing. It's something serious in your production. Tool breakage. In a number of cases, an accident, although in a big number of cases, an accident that could have been predicted, but people failed to predict it. In a number of other cases, it's a phenomenon that, is logical to take place if you look to the things that happened before. And learnings from this, I would say, if you see a broken tool, one, tool crash or tool breakage, direct split. Tool crash, that's something separate. Tool breakage, where did the tool break and when did the tool break? And based on those two observations, you can already learn a lot on how not to do it in the future. So in the future, you manage, I could end like this, that the number of broken tools in your workshop is perhaps not zero, but is at least in line with the industry standard, is at least as what we call good, acceptable. This is what it should be. Before we stop, let's first now see if we have some questions. Yes, a lot of questions, and I see one question is, any idea how to proactively manage stock material for consistency? Different supplier will introduce metallurgical variants and therefore cutting conditions will change. That's a tough one. The only way is in a big number of companies you have entrance check of materials coming in, especially the more expensive materials, titanium alloys, super alloys. People do some checks to see if the material is in line with specifications. The only really working way, I would say, is if you do entrance inspections, also do some entrance inspections on the properties of the materials that are important to know about from a machining perspective. Then you can predict a lot better. If that is not possible, another way is to teach, to educate your operators, your production engineers, to recognize or to be capable to observe a machining process in a more proactive way. What do I see and what does it indicate what I see? And if I see is an indication that something is going out of balance, so I can react and bring it back in balance by doing stuff. So entrance check of properties, features of your workpiece materials that are important from a machinability perspective for the materials, which are not always what people check when materials come in. For instance, if you take titanium, people say, yeah, I check the hardness. Now, trust me, hardness in titanium has nothing to do with the machinability of titanium. If you say, oh, the hardness is a little bit higher, I don't care if it's titanium from a machinability perspective. What I do care about is the thermal conductivity. That's a whole other story. But that people don't check. You understand what I mean with what is important? The other thing is well-educated, trained operators, production engineers from a machining physics perspective. Seen the time. One more question. Is tool breakage a bigger problem in some industries or in mass production or small batch production? Yes. Tool breakage is the issues with tool breakage is very strongly depending on the type of industry. The more complex the materials you machine, the more you will see issues with tool breakage. And sometimes in a very, very strange thing, in a very strange way, I take my titanium again. Titanium is not so hard than steel, yet you see a lot more breakage in titanium machining than in steel machining. That's why I said you have to understand the material. So the more complex your workpiece materials, and yeah, you can translate that to if you have an industry where they machine a lot of titanium materials, take the aerospace industry, you will find more breakage than in traditional general engineering. And it is, I would say, in small batch production, there are more issues with broken tools than in mass production. And the reason is rather simple. In mass production, the processes are much more prepared. There's time available to find everything out and controlled. There are very clear specifications also for the operators. Every X workpieces you need to replace a tool or whatever. While in small batch production, that's not there. There we have to count a lot on the operators, and in a lot of cases, yeah, that leads to not so good situations. Let me say like that. Seen the time. There are some more questions from a practical perspective. Whatever questions I find in the comments of this, I'll make sure you have an answer as quickly as possible. If you want to have a copy of this presentation, please let me know. And of course, we send you a copy of this presentation. If you want to have other information, some people say, yeah, what about the technical guides? Where do I find the technical guides and stuff like that? Let us know. We send you all the information you need, so you can find your way to all stuff. Thank you again. And as I said, this was the last presentation for this year. That means that we are close to the holiday season again. On behalf of my two colleagues, Alesia and Margarita, first of all, thank you very much for participating in these events this year. We are looking forward to see you next year again. We think we have some interesting points on the agenda again. If you feel that there are things you would like us to have a talk about, please feel free. All suggestions are very welcome. And as a last word, I would say we wish you a very nice holiday season and best wishes already for next year. Thank you very much, and looking forward to see you the next